All right, so sorry to those of you who are not here and are trying to look at the screen. I know there's like a rainbow banding. Some kind of like resonance between the projector and my camera. I really don't know how to fix it, but so sorry. I'll try to say in words where we are. I wanted to look at some pictures and some demonstrations I had at the start of chapter 2. So we're beginning our, this is really, I would say, where calculus honestly starts, because the first thing we need to know to do calculus is the concept of a limit. So what I want to do in the next few minutes is to try to describe to you why we need a limit, all right? And so we'll soon see that this concept allows us to give like careful definitions of things like hole in the graph, a vertical asymptote, even a finite jump discontinuity. Like all of these things, we have careful definitions in terms of limits. So that's in and of itself interesting, but what's really interesting is what it has to do with a tangent problem. So let me go down here. So first of all, let's talk about the tangent for a circle. So I think I mentioned this like day one. If you think about a circle, what happens? You have just, oh goodness, no! I have been, the hyper scrolling has got me. Hey, come on in.
Sorry.
You're fine.
Yeah, I have class until now.
I understand. Just this week though, right? Right? That's just this week, right?
No.
Every week?
Yeah, every week.
Oh, maybe you need to change the other section then.
Yeah, I did. This was the best option I had.
Well, but you can't be missing an hour every week.
Yeah, well, that's it also.
That we need to fix that. I thought you were saying it's just this once. Oh, no.
This class was just like 5 times this semester or something.
No, this is every week, yeah. And we'll have tests in here, I think, certain Wednesdays, so I can't remember. But anyway, we're in chapter 2, so once you get the notes open, you can follow along. But so we're talking about like the.
How do you log in there? Is it?
Oh, same as anywhere else. So is your username there?
Yeah.
So.
The password is something else, right?
Whatever it is for you. I can't tell you your password.
Yeah, that's what it was. Okay.
So is it loading?
Yeah.
Okay. So the tangent to a circle, right? There's just that one point where it meets the circle, right? And then it just kind of goes off, right? So that's the idea of a tangent. And so I made a little demonstration with this, Desmos software. So, so you can actually move it around. See? So there's I move the point of tangency, the line goes with it. So, or if you want, you can animate it. Check it out. And if you play around this website, it's pretty fun. Like you can visualize a lot of different functions and graphs and things, and even look at different cases using this Desmos software. We'll use this in our labs, among other things, okay? But, all right, so getting back to my, so that's the idea of a tangent line, right? For a circle, this is something we've studied since like the time of Euclid. So it's been a few 100 years that we've done that. Now, if we think about something like, stop that. If we think about a graph that looks like this, though, oh, thanks. Cool. So we're in, if you click on limits, it'll take you, yeah, we're there. So
I'm completely new chapter.
Yeah, we're in chapter 2. So now, a point like, so if the functions, if the shape is not a circle, and you talk about a tangent line. So with a circle, we can talk about a tangent line as being the one that just goes through the one point and only that point, right? But that definition isn't going to work other places because, like, here's a function, right? Here's a tangent line, and as you can see, it's 1, 2, 3, 4, 5 points of intersection with the graph, right? So whatever a tangent line is, it's not just a line which intersects the graph at one point. It's something more than that, right? Like, what is a tangent line? What do we mean by that? I would say what we mean is we want a line that meets the graph at that point, right? And it matches the graph close to the point, right? It's like the best linear approximation to the graph at that point. Let's move the point around. I'll show you more. I think I have a link here. Ooh, I've animated it. Let me stop that. Pause. So as you can see, if we move the point of tangency, the tangent line, see the tangent line? It like matches the graph. It's the best line that you can fit through the graph right there. This is the idea of a tangent line, right? So if I can move it around here, see how it goes? So notice like the tangent line at the top of a hill, what can you say about the tangent line? See, the tangent line is like horizontal at the top of a hill or at the bottom of a valley, right? So there's that. So if we were looking for places where we had maximums or minimums in our function, what would we be looking for? Places where the tangent line has like slope 0, right? That's something we'll come back to as we go on. Any questions? So I'm trying to motivate what a tangent line is and why it matters to this concept of a limit I'm about to define. So you can play around with this if you want. All right, so I had a couple of in-class exercises here just to try to remind you guys about how we work with lines. All right, so I'll stop my projecting here for a second. And actually, let me finish the projecting and then we'll come back and do these in-class exercises so that otherwise it's kind of awkward. We'll come back to these, okay? Okay, so how should we define the tangent line at a point carefully, right? Well, I would say we want the tangent line to go through the point. So as we'll see in the in-class exercises, will soon work. Sorry, if I could follow my own instructions, it would be more natural. But just the classroom setup here has me going on. Sorry, but we'll soon review lines, and so this makes more sense. But if you want the formula of the line to go through the point A comma A, this is a nice, using the point slope formula. You put the y value there, you put the x value there, and this formula is going to give you a line which goes through the point A comma f of A and has slope m, right? So it's easy to make a line go through a point using the point slope formula for a line. But choosing that m, like what slope should the tangent line have, right? And if you look at this picture here, you can kind of start to get a sense of it. Here's a picture of a secant line. I'll look at the demonstration page because that kind of brings it alive more. All right, so here, let me explain what we're looking at. So I'm looking at the point of tangency being A at 1, right? What we're looking at with this blue line are secant lines. The secant line is the line that just connects the point of tangency in this case, to another point on the graph, right? And you can calculate I'll stop it from animating here. You can calculate like the slope. Here, I'll do a simple one. What's the slope of this secant line? This is kind of a stupid one. Yeah, the slope of this secant line is 0. Otherwise, it's hard for me to calculate. But you can see that the secant line does what? It gets closer and closer to that tangent line, right? As your point B gets closer and closer to A, right? So as you approach the point, as the secant line is calculated for points closer and closer to the point of tangency, you're getting closer and closer to that tangent line that you want to capture, right? So if we could come up with a rigorous meaning of that word limit, we could say that the tangent line is the limit of the secant line, whatever that means, all right? Now, going back to my notes again here, this right here, folks, is the formula for the secant line. This is basically using the two-point formula for a line. You know, we get the slope, the difference of the y values divided by the difference of the x values. That gives you the slope, and then this puts it through the point a comma f of a, right? So this is the equation of the secant line. So what was I just saying about the tangent line and secant? I said as the point B does what? Gets really, really close to A, the secant line gets really close to the tangent line. So look at this, look at the slope. This is the slope right here, right? F of B minus f of A over B minus A. What happens as B gets really close to A here? We get B minus B. We get division by 0 as A goes to B there, right? But what happens in the numerator? We get f of B minus f of B just the same, right? So we also have a 0 upstairs. So if you think about this process, it's something like 0 over 0 as the point approaches the point of tangency as B goes to A. Now, if it were just division by 0, there'd be nothing to fix it. But the fact that there's a 0 upstairs and a 0 downstairs, it's the balance between those two things for certain functions that allows the tangent line to exist. So like whatever that works out to as you're approaching, that's the slope of the tangent line. Now, what I'm saying right now is very fuzzy, right? I mean, you can see the picture. I think if I gave you a graph and I gave you a point and I said, to the best of your limits of your artistry, graph the tangent line, I think you guys could do that, right? You could take a ruler and you could try to make the line match up with the graph as close as you could to kind of match the slope. That'd be the tangent line, right? Maybe you've done that in a science class, sort of, right? It's kind of similar to the idea of like best fit line for data. You know, you're trying to find the line that's closest to the thing you're looking at. But, so my point to you is that the m, that's the slope of the secant line, it has to be defined in some sort of limiting process, right? F of B minus f of A over B minus A, that should be the slope of the tangent line. But what can you say about this limiting process? As B approaches A, let's think about it. Can it allow for A to equal to B? Like it can't actually do that, because if it did that, we'd have division by 0. So whatever this limiting concept we're talking about is, it must be constructed so that it considers values close to the limit point, but not the point itself. Because if it actually got to the point itself, it wouldn't serve the purpose that we need it to serve. Right? So a limit is something that investigates points close to the limit point, but not the point itself. So that's why at section 2.2, I give a definition of limit point. See here? A limit point, I know this looks like hieroglyphics, but let me just kind of distill it. What this is saying is P is a limit point if, when you intersect the ball around the point, not including the point itself, there's an intersection with the domain, and it's non-empty. And that happens for every delta greater than 0. So what this is just a fancy way of saying that close to the point P, there's infinitely many points close to that point. They could be to the left, they could be to the right, they could be on both sides. All right. Now, if there's points included to the left and to the right, then it's called an interior limit point. All right. And so, pretty much it. Now, there are functions that don't have any limit points. An example would be like a sequence. A sequence has a domain which is natural numbers. And so there, like, points in the domain are separated, like 1, 2, 3, and those kinds of points are not limit points, because if you take a ball around it like 1, there's nothing else in the domain for a sequence. So that kind of falls outside our scope in here. We're looking at functions of a real variable, not so much sequences, okay? But, so example 2.22 is really just is just a cautionary tale. Like the scope of our discussion is not including, really not aimed towards sequences, all right? And then here it is. Here's the definition of a limit, all right? Let f be a function with interior limit point a, and suppose L is a real number. We say that f of x goes to L as x goes to a, if and only if for each epsilon greater than 0, there exists a delta greater than 0, such that for all x with 0 less than absolute value of x minus a less than delta, it follows that the absolute value of f of x minus L is less than epsilon. In the case that this condition's met, we say that the limit exists, and we denote it by limit as x goes to a of f of x is equal to L. All right, I'm going to write this again on the board once I put this away, all right? But I wanted to look at some pictures with you before I do that. So what's going on here, think about this. What does it mean, 0 less than absolute value of x minus a less than delta? What does this inequality here say? It says, what is the 0 less than? That means that x is not equal to a, right? X equals to a gives you absolute value 0. So we don't have to consider that. That's what I was just talking about. We don't actually consider x equal to a in the limit as x approaches a. So we consider things close to it, like within delta units of it. And if they're that close, then we have to be able to make them, I mean, for each possible distance, epsilon, from the limiting value, you have to be able to pick inputs that give you outputs which are that close. So basically, now this picture isn't quite accurate because the blue band, which describes the delta, really should have like a missing line right down the middle. At A itself, there should be like a dotted missing, because we don't consider A. All right, so my picture is a little bit wrong, because there should be like a missing center dotted thing, all right? But basically, that's what's going on is, if you're looking at this limit, you're saying, if I pick this green band, I can make a blue band which is skinny enough so that the graph fits in that little zoom box. That's what this definition is saying. That's all it's really saying. So I think with that, I'm going to turn this off, and we'll sort of look at it on the board. All right? So we're actually not going to do anything else with lines today. So I think what we're going to do is we're going to postpone those line examples until later when we actually look at the tangent line. Then I'll try to remind me to come back to those when we get there. I do think those are good for us to do when we start talking about tangent lines, because you guys could use a review of equations of a line. But that actually is detached from everything else we're doing. So let's just, focus on the limit business here. We won't get back to tangent line today, I don't think. So I was talking about the tangent line to try to motivate why the limit has to consider points close to the limiting point, but not at it. All right, so first things first, let us write the definition. If A is a limit point, rather an interior limit point of f, and L is a real number, then we say f of x goes to L as x goes to A when, well, let's say if the following holds. All right, so here it is. If for each epsilon greater than 0, there exists delta greater than 0 for which 0 less than absolute value of x minus a less than delta implies absolute value of f of x minus L is less than epsilon. This is the so-called epsilon delta definition of a limit. Now, I'm going to try to put the lion's share of our effort here on graphical and algebraic argument-based analysis of limits, but at the start, I need to give you this definition so that we can be honest with each other and give you the real definition, all right? And we'll work an example or two using this definition, but it is a pain, and it usually vexes students, but there are some examples we can do that are really quite elementary for this. So let me show you what I mean by that. So here's an example. I mean, this is in-class example 2.2.4. This is page 53. All right. Anyway. So you're supposed to show that the limit as x goes to a of x is equal to a. All right, that's the task at hand here. Now, I seem to have neglected to say here also write the limit as x goes to a of f of x equals to L. So you can either write f of x goes to L as x goes to a, like that sentence, or you can write that limit with x going to a, f of x equals to L. Those have the same meaning. It's like just shorthand for the same concept, and they're both abbreviations for this more complete technical, logical implication here in terms of inequalities. Now, all right, so let me talk about it. So here we're going to let f of x equal to x, right? That's the function we're thinking about. All right. This function has domain all real numbers. So every point, in fact, for this function is an interior limit point. So we can definitely calculate the limit. Like this initial sentence, it's all fine. There's nothing to think about, really. So if a is a real number, then it's a limit point, all right, for f. Let me just get to it. I'm sorry, I'm writing too much. So we're thinking f of x is equal to x. We're thinking a is like an arbitrary point, all right. Here L is equal to a, right? This is we're claiming that the limit as x goes to a of x is equal to a. All right, so here's the proof. Let epsilon be greater than 0, and choose delta equal to something. All right? I'm going to let us fill in that blank. Right. If 0 is less than epsilon value of x minus a is less than delta, then note the epsilon value of f of x minus L, which in this case is equal to x minus a, is less than epsilon. Thus, the limit as x goes to a of x is equal to a. So I'll let you guys catch up here. What do you think? So you got to fill in the blank. What should we make epsilon? What should we choose delta to be in this case? Ah, hey, well, you know. Now I feel dumb. Working in the dark for nothing. See, this is we get control here. Basically, we want to like put something here that forces this to happen. So generally speaking, when you're working the proof out, this delta will be like some function of epsilon, generally speaking. Now this one, but we just make delta equal to what? All right, yeah? Equal to, no, 1 won't work here. There is a problem 1 will work for, but not this one. So I'll put you guys out of your misery. What if we just make delta equal to epsilon? Right? If we make delta equal to epsilon, and we can do that, then if 0 is less than x minus a is less than delta, and delta is equal to epsilon, what does that tell us? That tells us that f of x minus L is less than x minus a. I mean, it's equal to x minus epsilon value of x minus a is less than epsilon. And that's all I need to prove, that's what it means, to prove that the limit as x goes to a of fx is equal to L. So that proves it. So anyway, there you go. Here's your first limit law. Woohoo! The limit as x goes to a of x is just a. How about this one? The next dice. 2.2.5. Now we're supposed to try to show that the limit as x goes to a of x squared is equal to a squared. Can we show this? All right, so let me just kind of show you some scratch work here. All right, so we are going to want to have epsilon value of f of x minus L is x squared minus a squared, right? Less than epsilon, right? That's what we want. That's our goal, right? Now, this is what? Can we factor? That's x minus a times x plus a, right? Now, okay, so that's epsilon value of x minus a times the epsilon value of x plus a, right? Now this we got control of. That we can make less than delta. That's what we assume. We get to control how close we are to the limit point in the argument by choosing delta carefully. But this x plus epsilon value of x plus a business over here, That's kind of a drag. I don't know what to do about that. Now we do know that the so let me show you a trick. For this one, if we have absolute value of x minus a, right? If we knew that that was less than 1, what would that tell us? This would tell us minus 1 less than x minus a less than 1, right? Which would then tell us what? I feel like I'm forgetting something. I didn't think I needed to get into this for this one. I'm bothered at the moment. I'm being dragged into. If I'm going to do this sort of thing, let me. No, stay the course. I'm going to stay the course. Sorry. Then I can add what can I do? To get to x plus a, if I add 2a, right? 2a minus 1 less than x plus a less than 1 plus 2a, right? So I'm not sure. I guess if I said let m equal to the max of the absolute value of 2a minus 1 and 1 plus 2a, right? If I make that the maximum of those two things, then I think you can argue that that implies that minus m is less than x plus a is less than m. If you think about it.
So you can answer with a range.
I'm getting there. It's complicated. Let me finish it. I started it, so I'm going to finish it. But I'll be confess, I'm regretting this at the moment. There's a simple argument for this one that I've forgotten at the moment, and so this gives me that this means that the absolute value of x plus a is less than m, right? So if I have this condition, right? And I define m as such, then I can control the size of x plus a as at most m. And m is a positive constant, right? So with this ball of wax right here, I could make this less than what? Less than delta times m, right? Because this is less than m, and I get to make this less than delta in the proof. In the definition, there exists a delta greater than 0 such that this condition implies that. So we assume this to try to get that. So at the moment, I'm trying to develop a scheme, a strategy for how to choose the delta, and this one's complicated, admittedly. So here it is. Let epsilon be greater than 0. Choose delta equal to the minimum of 1 and epsilon over m, where m is the maximum of the absolute value of 2a minus 1 and 1 plus 2a. I think it's clear that m cannot be 0. If m is 0, I'm in trouble, right? Because I'm dividing by m. All right? Then if 0 is less than absolute value of x minus a, is less than delta. Well, delta is less than or equal to 1 by construction. Right? That's the trick. And so then what? Then thus, you know, the absolute value of x minus a is less than 1, which implies that, of course, 2a minus 1 is less than x plus a is less than 1 plus 2a. Hence, the absolute value of x plus a, and of course this is less than m. Sorry, I'm trying not to write too much. It follows the absolute value of x plus a is less than m. And admittedly, I'm using by scratch work. All right, so I try not to do that. Sorry about that. If this was a real analysis class, I'd be worried I'm misinstructing you here, because I would expect you not to do that in your proof. This is not a real analysis class. I will not ask of this you on a test or a quiz or anything. This is just for your reference. Like I was saying, I regret this. This got too hard for us. But I'm this far in, I got to finish. So absolute value of x plus a is less than m, right? Yay. Consider then that the absolute value of x squared minus a squared is what? Absolute value of x minus a times x plus a, right? Which is equal to absolute value of x minus a times the absolute value of x plus a. And that is, by assumption, less than delta times m, right? But we constructed delta to be the minimum of 1 and epsilon over m. So that means delta is less than or equal to epsilon over m. So the m's cancel, as was my plan, and you get epsilon. So what I've shown, to recap, is that for each epsilon greater than 0, you can choose a delta greater than 0. This is greater than 0, all right? For which, if we're within delta units of the limit point, we're within epsilon units of the limiting value for the output. Therefore, the limit as x goes to a of x squared is a squared. All right, so this will be the last epsilon delta we do in here, except for, like, I'm going to show you a proof of a couple properties there I have to do epsilon deltas, but I will try not to belabor this much more. Any questions? I mean, please don't ask questions.
It's not bad to struggle just a little keeping up with that, right?
Oh yes, no. This is like hard.
Okay.
This is hard.
I was just making sure because I was like, I probably don't need to be in here.
No. This is not where the course is. This is just where the definition took us today. Let me get back to where the course. Let me get back to where the course is. Okay. So I needed to give. I feel obligated to give you the definition of the limit, because I think when it's left out, it leaves a gap in the discussion. But in truth, we're going to be able to calculate limits by limit laws, all right, which we'll talk about next class, limit laws, and graphical means, all right? So, I have 3 examples on 53, which I'll put up on the board here. So let's talk about graphical understanding of limits. So let me say it this way. We could always fall back on like the epsilon delta kind of arguments, right? We could get back to that level for all of these things. But I think I want you to know that that can be done, right? But do you want to do it? I think the answer is no, right? Not at this point in your mathematical career, right? So let's see here. So here's one. I'm just going to tell you what we write in this one. This is at 2. This is at 2. So only one of these examples here has a limit at 2 which exists. So in each one of these cases, each one of these graphs, 2 is a limit, an interior limit point of the function. I'm graphing y equals f of x in each case, all right? Y equals f of x is graphed. So 2 is a limit point in each one of these because 2 is in the interior of the domain. There's like points to the left and to the right at 2. All right. So we can at least try to calculate the double-sided limit in each one of these. So in this one here, right, let's start with a positive. The limit as x approaches 2 of f of x is equal to 3 from what I have graphed there, okay? But notice that 2 is not in the domain of the function, right? So the limit of a function allows us to get to points which are outside the domain. That's something that's really different about the limit. It's not just like evaluation of a polynomial. We can get the points where we don't have the function defined. But you can still see it, right? As you're getting closer and closer, it gets closer and closer to 3 from both sides, so the limit's 3. This one here, the limit as x approaches 2 of f of x does not exist. Because it's going to 3 from one side, but it's going to 0 from the other. So when we tried to satisfy that epsilon delta condition that we're looking at, you wouldn't be able to do it. And this one here, well, that's even worse, right? It's going to minus infinity from one side, it's going to infinity in the other, right? So this also has a limit as x goes to 2 of f of x, which does not exist. Right? So we should introduce some notation for what are called left and right limits, all right? So we can talk about, let's start with the middle one. Let me just tell you here. So the limit as x approaches 2 from the left, see that minus? From the left of f of x. Well, so like as x from the left, you're approaching to 3. But the limit as x approaches 2 from the right of f of x is what? What's that? Now, the limit refers to the y value, like f of x, taking the limit of f of x. Limiting value refers to the values of the function, the y in the graph. So what is it? As x approaches 2 from the right, see that? We're going to this point right here. No. 0. Now this one, we could also talk about the double-sided limit. We talk about the left to right limits. As 2 approach 2 from the left, we get 3. From the right, we get 3. Right? And how about here? What would you like to say? The limit, you guys tell me. What should I write here? Limit as x approaches 2 from the left. What would that be equal to in this one? Negative infinity. We have a winner. And how about from the right? So now, I haven't written the definitions of these kinds of an infinite limit on the board, right? But it's in the notes, okay? And the definition is like kind of just what you'd think it is. Like a limit is going to be infinity if you can make the value of the function as big as you want by getting as close as you need to the limit point. In other words, the values of the function grow without bound if you get arbitrarily close to the limit point. And these left and right limits, they can be defined carefully in terms of inequality statements. So you're just considering points to the left or just points to the right of the limit point, but arbitrarily close. That's what the left and the right limits go, all right? Now you can talk about left and right limits at like the boundary point of a domain of a function. Right? So like we could look at the square root function. We can talk about the limit of the square root function at 0. Right? So what's the square root function look like? It looks like this, right? So it makes sense to talk about the limit as x approaches 0 from the right of the square root of x. This is a meaningful limit. It's well defined. The answer is 0. I could prove that with epsilons and deltas if we all had much more coffee, you know, time, I don't know. But on the other hand, this limit would be utter nonsense. This is not a well-posed limit. It's not well-posed because 0 is not a right boundary point of the domain of the square root. Like, there's no points to the left of 0 which are in the domain of square root. So we can't take that kind of limit. There's nothing to limit on. But think about this. So for an interior limit point, when you do have points to the left and to the right, you have 3 different behaviors described by limits. This is a hole in the graph. So a hole in the graph is a point where the right and the left limits both exist and match. When they match, it's a hole in the graph. If the right and the left limits both exist, but they do not match, what's that? That's what we call a finite jump discontinuity. So this is a jump discontinuity. Often finite jump discontinuity, right? And how about this first case? If either of the right or the left limits, or both, are infinity or minus infinity, that means that the function has a vertical asymptote at that point. Right? So we can describe these different behaviors carefully using limits. So on page 54, I have, careful definition for right and left limits. And I have a theorem which says that the double-sided limit, all right, exists if and only if the left and the right limits both exist and match. All right? The proof of that is not especially exciting, and so I've relegated it to an appendix in the notes. I haven't even put it here for you to read, okay? In-class example 2.2.9. Let's do it. I think we'll stop here for today with this 2.2.9 in-class example, okay? Okay, so here we go. Oh, wait a minute, that doesn't make sense. Like 10, 11, no. Let's try 6. 2, and let me put some coordinates on that. That's all right. So here's the problem. Find limit double left, right, and double-sided. Sorry, my handwriting is very bad up here. For A equal to minus 2, 2, 6, and 10. Or say not not well posed. So okay, so how about this one? Definitely, we can't calculate the double-sided limit. I mean, the limit as x approaches minus 2 from the left of f of x. Yeah, not well posed, right? Yeah. Could we say it's a poser? I don't know. But as far as I know, poser is not a mathematically defined term. Anyway, so that's no good. And if either the left or the right limit is not in play, then we can't talk about the double-sided limit, right? So likewise, the double-sided limit doesn't make sense there. But we can calculate the limit as x approaches minus 2, and the upper plus, the superscript, refers to either coming from the positive values of the limit are coming from the negative values of the limit. So minus from over here, plus from over there. So that's like this. And so I think that's equal to minus 1. Yeah. How about at 2? What do you got? I should mention there's another notation you can use, which is this. We can also write this: f of x goes to 3 as x goes to 2 from the left. That's how to write that kind of limit as a sentence rather than the limit notation. This is equivalent to saying the limit as x approaches 2 from the left of f of x is equal to 3. This is equivalent to this sentence right here. So how about the other side? F of x goes to what as x goes to 2 from the right? It's going to 1, right? So how about the double-sided limit here? So in this case, we would say the limit as x approaches 2 of f of x does not exist because the left and the right limits disagree. These kind of problems I do expect you to be able to do, right? I think the epsilon delta stuff is like, come on, that's like a little bit much for Calc 1, right? But this kind of reasoning, you need to kind of acquire. How about at 6? What we got? Limit, I don't want to write it down, but the limit as x approaches 6 from the left is equal to the limit as x approaches 6 from the right. They're both what? Infinity, right? So the limit, in fact, we can write the double-sided limit is equal to infinity in this case. If the left and right limits both exist and are infinite, both positive infinity, I like to call it a volcano. It's like, right? And how about at 10? What do we got? Limited as x approaches 10 from the right is equal to the limit as x approaches 10 from the left is equal to the limit as x approaches 10 from both sides. And what is it equal to? I told you this point. 2.7. Yeah, 2.7. So sorry to scare you in the middle of class with the epsilon delta stuff. I hope this is less, troublesome. We are going to be learning the limit laws and how to calculate limits using algebra steps as we go forward, okay? So like all that stuff we were doing on factoring, it's going to come back into play. And algebra we haven't gone over yet, too. You'll learn all kinds of algebra. Oh, man, I was going to end the class early. What happened? So sorry, guys. One of these days.